All right, can you hear me back there? Yes? Okay. Thank you. I just want to thank Mahesh for this very kind invitation. And let me first start by saying that this is going to be a change of gears, a significant one, relative to the kind of topics that we have been listening to for the past couple of days. In that, just like Sibendo was saying this morning, I also happen to be sometimes considered either too biomedical in the kind of work that I do or too engineering oriented, which puts me in this intersection that is usually a pretty good place to be. I hope that after I present you this brief talk, I can convince you that there's a lot of the issues that you have talked about during these couple of days that could be very easily translated to the kind of problems that groups like mine and others are facing in the use of sprays for medical problems. Okay, I need to apologize since this is somewhat improvised. I have to borrow some slides from a talk I gave 3 months ago at the ILS Europe. So some of you might have seen these slides before, but most of you haven't. So let me very quickly tell you about the rough picture about the use of sprays in medicine. Maybe some of you have heard that there's quite a relatively significant amount of work in the area of respiratory system delivery, or sprays are being used as drug delivery mechanisms. And there's quite a bit in terms of stent coating, for example. There's a lot of work in respiratory systems, etc. Also for ophthalmic drug delivery in the industry of body lotion sprays, pumps. There's, again, a lot of work. My area is somewhat different, and here's my plug. So please excuse me. This is a plug of just a recent paper that was published in the very last volume and issue of Atomization and Sprays this year. This is a review paper that Corinne Lexfeld and I put together, trying to draw some attention from this community to the kind of problems we're facing. As you probably know, if you know her work, she concentrates mostly on the respiratory drug delivery kind of things. And then, as you will see, I work mostly on the therapeutic use of sprays. So if you have some curiosity, I have the PDF file of this paper, and I can share it with you right now. All right, so very briefly, the kind of projects that relate to sprays that I do in my lab span all the way from droplet impact dynamics. That would be sort of my fundamental side of it. Flash boiling atomization, spray formation. But they're mostly driven by the kind of application that you see here at the bottom. These are dermatologic diseases. They're normally treated with lasers. And we use sprays for the purpose of cooling the skin and maintaining a good thermal control of the skin during laser procedures. Okay, so this is an example of a skin disease known as port wine stain birthmarks. And I was fortunate enough during my postdoc time to work at the Beckman Laser Institute at UC Irvine. And under the guidance of Dr. Nelson, we developed, or we improved the development of spray systems that are now used to treat these kind of diseases. And I'll just briefly go through that. That's not the only disease that requires this kind of thermal control. There's others like telangiectasias, hemangiomas. These are the port wine stains that I mentioned. There's other kinds of diseases. These are vascular lesions. These are what are known as pigmented lesions. But all of them share in common that can be treated with lasers, with different kinds of lasers. And they require a very strict thermal control. So here's where sprays become really, really handy. And in the cosmetic world, there's a tremendous amount of opportunities. And quite frankly, there's where the money is. Okay? A lot of these research in these areas get funded because of the cosmetic industry developing systems that can be applied to both kinds of issues. So very briefly, the main idea in the treatment of this kind of disease and others is the same, where you're trying to take advantage of the preferential absorption that the blood has for certain wavelengths, and try to target your laser down underneath the skin surface to photocoagulate, what we call photocoagulate the vessels. But in that process, you want to avoid an excessive amount of absorption at the epidermal level, because that would cause severe injuries, all right, burning of the skin. And you just look at the absorption spectra of the main absorbers of the epidermis and blood, namely the melanin and the hemoglobin. And you can see that within the wavelength range of interest, the absorption is very similar. That's why you're having these pretty much a very similar amount of energy absorbed at the two levels. And that's why the problem is you can lead to irreversible scarring and dyspigmentation because of excessive epidermal heating. So here's where sprays came into play, and this was back in the mid-90s, where the idea was to accurately and very precisely deliver a short spurt of a cooling spray, and they called it cryogen sprays, but they really never used cryogens. They used refrigerants, R134A to be more precise. And the idea was to extract very rapidly heat from the epidermis so that by the time the laser is delivered, you already have an initial lower temperature. So you still have the same delta T in terms of the absorption taking place at the epidermal level, but now you're starting from a lower temperature. And you have to be very accurate and precise in time, because if you spray for too long or you wait for too long, that cold wave, so to speak, travels all the way down to the target, and now you have to fight against that initially lower temperature. So this proved to be very, very successful, and the patent that led to the development of this technology has already paid quite a bit of honorarium to the inventors. But the truth is that even up until now, the community still has issues like this. There's some partial improvement, but there's no total improvement. And much of it, not all of it, but much of it can be improved if we maximize the cooling effect of the sprays that we're using. So here's where a lot of the work in this area took place towards the early part of the 2000 years. For instance, we were playing with nozzles that we could control in terms of the opening throttle and timing, so that we could have some control on the spray cone angle, also on the mass flux, of course. We developed some experimental nozzles in the lab, and we looked at the different types of sprays that we could produce with what we called wide and narrow nozzles. So here are the dimensions that you can see, and conditions, and delivering always into environmental pressure, we had very significant changes in terms of the spray shape. And we later also took some information about the characteristics of these sprays. For example, solder mean diameter as a function of distance away from the nozzle. So we could see some variation, because these are very highly evaporating sprays. Okay, so for the people in the combustion community, you can see the analogies there. We're having these very, very volatile spray being ejected and traveling towards the surface where you're trying to cool really fast. Velocity measurements that we carried out also with PDPA systems that show significant variations over a relatively short distance. Temperature measurements with, at that time we were using a very rough multi-thermocouple sensor just to get an idea for how the temperature varied over that distance of interest. And this is really a temperature measurement of the mixture of the droplets with the surrounding gas phase. So it's not quite the droplet temperature, but it gave you gave us an idea of how low the temperatures could get. Now, clearly, here's where the connection can be made with the heat transfer characteristics of all these, because clearly, depending on which kind of sprays you produce, which of course depend on the kind of nozzle that you have, the end result in terms of the delivery on your surface is very different. If you have a relatively dispersed spray with what we call sometimes mist, you have this liquid cryogen layer that sort of boils very quickly, that right there at the region that you're trying to target, surrounded by the dry surface. Whereas when you have this very forceful jet, you have the opposite, right? And is this important? Yes, it is very important because we had evidence from the clinic that depending on how well those nozzles were designed, there were there was some injury, cooling injury, overcooling sometimes. We took then we developed some sensors to characterize the heat extraction as a function of time produced by these by these sprays, and we realized that yes, the angle of the nozzle was a very important parameter, and even if it was perpendicularly aligned with the skin, there were issues like deformation of the skin dynamically. Professor Abraham was talking about the impact on the surfaces that may also result in very different combustion dynamics. Or we have somewhat similar issues, but different in the sense that these are deformable surfaces. So they're deforming as the spray is impacting on them. Here, this was some sort of a practical solution to a problem where we wanted to dilate vessels. So we used vacuum suction cups to dilate those vessels and make them more susceptible to laser absorption. And the thing I wanted to show is that since now we're operating or we're delivering these sprays under a vacuum condition, then of course the thermodynamics of these sprays change a lot. So even if we had everything we wanted to know on, about these sprays for atmospheric conditions, now with this we had a different scenario. Here's an example. I think this is a very short video that shows exactly that deformation that I was talking about. And we never quite got to model that. We just knew that it was happening, and we tried to minimize it. We measured with some, what we call some tissue phantoms. We measured the variation of the heat flux as a function of time. With the suction cups, we had the opposite. Now, instead of having concave surfaces, now we had convex surfaces. So that also changes the condition of the surface of impingement. All right, let me see. There were issues also with humidity. Environmental conditions change as well. So there was some condensation that took place because we're delivering these sprays usually in atmospheric conditions that have certain degree of humidity. But once you have the suction cups added to your system, you're essentially delivering them without any humidity whatsoever. So you don't have condensation and freezing of water. So that changed all the boundary conditions. Penetration depth of these sprays also changed, of course, because of the pressure conditions. So let me quickly finish with other uses of the spray. So I'll talk to you about the use of these sprays to sort of overcome the excessive heating by the lasers. But we've also looked into applications where you can actually use the cryogens with a specific purpose of damaging the skin, temporarily at least. Why? Because, for example, if you do it in a combined way with some vacuum that stretches the skin after you have frozen just the upper layer, then the tissue becomes really brittle. And if you stretch it, you can create micro cracks, which become really good channels for drug delivery. So this is another idea we're pursuing right now as a new mechanism of drug delivery through the skin surface. Okay. These are some fluorescent images with some drug surrogates that we were working with. We showed, in fact, that even for very large molecular weights, these are molecular weights of 4,000 up to 70,000 kilodaltons, which are huge, huge molecules. We still got more penetration in the tissues that we were experimenting with. And even we went all the way to a human study to show that we actually got penetration down the cracks that we induced by these, what we call the cryopneumatic approach. I just want to, I think this is my last slide, just want to leave you here with some intentionally for cryosurgery purposes. This is related to this. What you see here are, of course, animal studies where we've shown that with a good combination of either a cryoprobe or a spray and a laser, we can control the propagation of the frozen tissue to wherever we want and pretty much establish a steady state situation where that frozen boundary stays where we want, which is something that currently, doctors cannot accomplish. This is a wild thing we did with fungi treatment, also using a combination of cooling and heating with lasers and sprays. And then more recently, we're also looking into using cavitation bubbles to create some jets that could perhaps be used to deliver drugs through the skin or any other tissue with relatively simple laser devices. So I'll stop right there because I know I'm out of time, but I'd be happy to answer any questions if you have any. Or if